There is a machine drifting above you right now. It has been there for over 3 decades. It weighs about as much as a large school bus. It travels at roughly 17,000 miles per hour, completing one full loop around the Earth every 95 minutes. And for most of its life, it has been staring, not down at us, but outward, into the dark, into distances so immense that the numbers required to describe them stop feeling like numbers and start feeling like mythology. That machine is the Hubble Space Telescope. And before we talk about what it saw, before we talk about the images that rewrote textbooks and the data that kept cosmologists awake for years, arguing over what it meant, we need to spend a moment understanding what it actually means for a telescope to die. Because Hubble did not explode. It did not crash. It did not go dark in a single dramatic moment the way a star does, collapsing inward under its own weight in a fraction of a second. Hubble's dying was slower than that. It was the dying of a machine that has been in space since 1990, that has been battered by radiation cycles and temperature swings between -200 and +200 degrees Fahrenheit every single orbit, that has had its gyroscopes fail and be replaced and fail again, that has watched its own components age in an environment that is utterly hostile to the concept of longevity. By the late 2000s and 10s, Hubble had already lost several of its original instruments. Its gyroscopes, the spinning mechanisms that allow it to lock onto a target and hold steady during long exposures, had been reduced from the original 6 down to a critical minimum. In 2024, NASA announced that Hubble would enter a reduced science mode, operating on a single gyroscope to preserve what remained of its stabilization capability. This was not a sudden decision. It was the result of years of watching the telescope degrade, a slow motion accounting of what was left and how long it could realistically last. The Hubble Space Telescope is dying, not dead. But the clock that has been ticking since its launch in April of 1990 is now counting down to something it cannot escape, the point at which the laws of orbital mechanics will pull it back into the atmosphere, and it will burn. NASA estimates that without a reboost, a mission to push it into a higher orbit, Hubble will re-enter Earth's atmosphere sometime between 2030 and 2040. The most likely window, based on current projections, sits somewhere in the mid-2030s. There have been discussions about a commercial servicing mission to raise its orbit and extend its life. But as of the time this video was made, those discussions remain discussions. So we have, at best, a decade, maybe a little more. And the question that should be keeping you awake, the question this channel was built to sit with, is not just when Hubble dies. It is, what did it see in its final years that we almost missed? What data came through that aging instrument, through those failing gyroscopes, through that battered 2.4-meter mirror that was famously flawed when it launched and had to be corrected with what was essentially a pair of space contact lenses? What came through all of that, right at the edge of its operational life, that changed what we thought we knew? And then, what happened when the James Webb Space Telescope looked at the same things? Because that is the real story here. Not just what Hubble saw, but what Webb confirmed. And in some cases, what Webb confirmed turned out to be far stranger than what Hubble had suggested. This video is a countdown. Not the countdown to Hubble's death, though that clock is running in the background of everything we're about to discuss. The real countdown is the one embedded in the discoveries themselves. The timeline from observation to confirmation. The years between Hubble sending back data that didn't quite fit the existing models and Webb arriving in its orbit 1 million miles from Earth and saying definitively, yes, that was real. Yes, something is wrong with what we thought we knew. Yes, the universe is stranger than the equations predicted. We are going to move through 5 major discoveries, 5 moments where Hubble, in its aging years, looked at something and came back with data that raised more questions than it answered. And for each one, we are going to follow the timeline forward through the years of debate, through the launch of Webb in December of 2021, through its first observations, to the moment of confirmation. Some of these confirmations are beautiful, some of them are deeply unsettling, all of them are reshaping cosmology in real time. Let's begin at the beginning, or rather, let's begin at the most fundamental disagreement in modern astronomy. There is a number at the heart of the universe. It is called the Hubble constant. And the fact that it carries Hubble's name is not a coincidence. Edwin Hubble, the astronomer the telescope was named after, was the first person to measure it, or rather, the first person to measure something that we now understand to be a version of it. The Hubble constant, written as h0, is the rate at which the universe is expanding. Specifically, it describes how fast a galaxy is moving away from us for every megaparsec of distance between us and that galaxy. A megaparsec is about 3.26 million light-years. So the Hubble constant tells you, for every 3.26 million light-years of space between us and a distant galaxy, how many kilometers per second faster is that galaxy moving away? The number Edwin Hubble measured in 1929 was about 500 kilometers per second per megaparsec. He was off by a significant margin, we now know that, but the conceptual discovery was seismic. The universe was not static. It was expanding. Every galaxy was moving away from every other galaxy, and the farther away a galaxy was, the faster it appeared to be receding. This was the discovery that led, when you run the expansion backward in time, to the concept of the Big Bang. If everything is moving apart now, then everything must once have been together. For the rest of the 20th century, cosmologists worked to pin down the exact value of h0. It mattered enormously. The expansion rate determines the age of the universe. It constrains models of dark matter and dark energy. It is one of the foundational numbers of cosmology, the kind of number that, if you get it wrong, means your entire model of the universe is off in ways that compound across every other calculation. By the time the Hubble Space Telescope launched, the best estimates for h0 ranged from about 50 to 100 kilometers per second per megaparsec. That is not a small range. That is a factor of 2. And within that factor of 2 lived decades of professional disagreement, competing measurement techniques, and more than a few careers staked on being right. One of Hubble's primary scientific missions, one of the reasons it was built, was to resolve this. To measure distances to galaxies with enough precision to finally nail down the expansion rate. To do that, astronomers used something called Cepheid variable stars. Cepheid variables are stars that pulse. They expand and contract on a regular cycle, and their brightness rises and falls with that cycle. The crucial property, discovered by astronomer Henrietta Swan Leavitt in 1908, is that the period of a Cepheid's pulsation is directly related to its intrinsic luminosity. A Cepheid that takes 30 days to complete one pulse cycle is intrinsically brighter than one that takes 10 days. This means that if you measure how long a Cepheid cycle takes and you know how bright it actually is, and then you measure how bright it appears in the sky, you can calculate exactly how far away it is. It is a standard candle, a light source, whose intrinsic brightness you know, which allows you to determine distance from apparent brightness, the same way you can estimate how far away a streetlight is by how bright it appears. The Hubble Space Telescope spent years measuring Cepheid variables in dozens of galaxies. Its resolution was good enough to pick out individual pulsing stars in galaxies tens of millions of light-years away. By the late 1990s, the Hubble Key Project, a dedicated program to measure H0, had produced a value of approximately 72 kilometers per second per megaparsec. This was considered a triumph. The factor of 2 uncertainty had been cut down to about 10%. But then something uncomfortable happened. A completely different method of measuring H0 using the cosmic microwave background, the faint afterglow of radiation left over from the early universe, produced a different number. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and photons to travel freely. The European Space Agency's Planck satellite spent years mapping the CMB in extraordinary detail, and from those maps, cosmologists could extract a value for the Hubble constant, not by measuring how fast things are moving now, but by modelling the physics of the early universe and projecting forward. Planck's measurement, approximately 67.4 kilometers per second per megaparsec. Hubble's measurement, approximately 73 kilometers per second per megaparsec. The difference is about 8%. That might sound small, but both measurements now have uncertainties of only a few percent. They do not overlap. They are, within their respective margins of error, genuinely incompatible. This is what cosmologists call the Hubble tension. And in the years leading up to Hubble's operational decline, the telescope that carries the name of the constant itself spent its remaining years trying to understand why the universe seemed to be expanding faster than it should be. Here is the timeline. 2019, the SH0ES team, supernova H0, for the equation of state of dark energy, publishes a refined measurement using Hubble data. Cepheid variables type 1, a supernovae as a secondary distance ladder rung. Their value 74.0 plus or minus 1.4 kilometers per second per megaparsec. The tension with Planck is now at what statisticians call 4.4 sigma. In particle physics, 5 sigma is the threshold for claiming a discovery. This is close enough to that threshold that people start taking it seriously as something that might require new physics to explain. 2021. James Webb Space Telescope launches on Christmas Day. One of its first scientific programs, one of the highest priority observations on the list, is to verify Hubble's Cepheid measurements. Because the obvious question hanging over all of this is, what if Hubble was just wrong? What if the Cepheid measurements were systematically biased by something in Hubble's instrument, by the fact that in crowded star fields, Hubble couldn't quite resolve individual Cepheids cleanly enough and was averaging their light with nearby stars, skewing the apparent brightness? Webb is better than Hubble in the infrared by a factor of roughly 100. In the near-infrared, where Cepheids emit a lot of their light and where the effect of dust is reduced, Webb can pick apart star fields that were a blur to Hubble. If the Cepheid measurements were wrong, Webb would show it. February 2023. The SH0ES team publishes Webb results. They have measured Cepheid variables in the galaxy NGC 4258 and in the Large Magellanic Cloud using Webb's NIRCam instrument. The results are, and this is where the story gets genuinely strange, they confirm Hubble's measurements. The Cepheids Webb sees are consistent with what Hubble measured. The crowding bias is real but small, and correcting for it does not bring the local measurement of H0 down to Planck's value. The Hubble tension survives its first real Webb-era test. What this means is profound and unsettling in equal measure. It means that the tension is probably not a measurement error. It is probably not an artifact of Hubble's aging optics or its inability to resolve crowded star fields. It is probably real. And if it is real, if the universe is genuinely expanding about 8 to 9% faster than the standard model of cosmology predicts from the CMB, then something is missing from our understanding of the universe's history. Something happened between the early universe and the present day that accelerated the expansion beyond what the equations predict. Some physics that we have not accounted for. The candidates are many. Maybe dark energy is not the cosmological constant Einstein proposed. Maybe it changes over time, stronger in the past, weaker now, or the reverse. Maybe there is an additional species of neutrino, sterile neutrinos, that affected the early universe's expansion in ways we haven't modeled. Maybe there is something wrong with our understanding of how the distance ladder itself works, some systematic error lurking in the way we calibrate from Cepheids to supernovae. As of the time this video was made, no resolution has been found. The Hubble tension is the biggest unresolved problem in cosmology, and the telescope that first measured it precisely enough to make it a problem spent the last years of its active life accumulating more data on the question, handing off an argument it had helped start to the telescope that came after it. But here is what we need to sit with as we move forward. If the universe is expanding faster than predicted, if there is new physics hiding in that 8% discrepancy, then the timeline of the universe's future changes. Our models of how long before the universe reaches certain states, how long before the last stars burn out, how long before the expansion becomes so extreme that structures themselves are torn apart. All of those timelines are built on the expansion rate. A different expansion rate means a different clock. This is not a small thing. This is the universe telling us it has been running on a schedule we haven't fully decoded yet, and Hubble was the one that first held up the data and said, "Your clock is wrong." Now, let's go further back. Not backward in time, forward in distance, which in cosmology is the same thing. One of the most iconic images in the history of astronomy is the Hubble Deep Field. In December of 1995, the Hubble Space Telescope pointed at a patch of sky in the constellation Ursa Major. The patch was chosen because it was extremely dark, no bright stars in the way, no known galaxies cluttering the field. It was, as best anyone could tell at the time, a nearly empty region of sky. About 1/30th of the apparent width of the full moon, smaller than a grain of sand held at arm's length. Hubble stared at that patch for 10 consecutive days. The total exposure time was about 140 hours. When the image was processed, it contained approximately 3,000 objects. Almost all of them were galaxies at distances ranging from several 100 million light-years to more than 12 billion light-years. Some of them were the most distant galaxies ever observed at the time. And because light travels at a finite speed, looking at a galaxy 12 billion light-years away means looking at light that left that galaxy 12 billion years ago, when the universe itself was only about 1.8 billion years old. The Hubble Deep Field was more than a beautiful image. It was a sample of the universe's population at different epochs. It was a core sample drilled through cosmic time. Over the following decades, Hubble produced deeper and deeper versions. The Hubble Ultra Deep Field in 2004, the Hubble Extreme Deep Field in 2012. Each time, the telescope stared longer, compiled more photons, and pushed the detection of early galaxies further back in cosmic time. What those images showed was something unexpected about the early universe. The standard model of galaxy formation, built on decades of theoretical work, simulations, and prior observations, predicted that the early universe should contain mostly small, irregular, young galaxies. The logic is intuitive. Structure builds up over time. Small things merge into larger things. The galaxies we live in today, large spirals, massive ellipticals, are the products of billions of years of mergers and accretion. Go far enough back in time, the models said, and you should see the building blocks, not the finished products. Hubble's deep field observations broadly supported this. The galaxies at high redshift, the most distant, earliest ones, did tend to be smaller, bluer, and more irregular than nearby galaxies. They were consistent with being young, actively star-forming, not yet settled into the stable rotating disks of mature spirals. But at the very edge of Hubble's reach, things got strange. In the late 2000s, using the Wide Field Camera 3 installed during the last servicing mission in 2009, the final upgrade Hubble received before its operational decline began, astronomers started finding galaxies at redshifts above 8 that seemed too massive, too structured, too grown for how early in cosmic history they were being observed. A galaxy at redshift 8 is being seen, as it was roughly 650 million years after the Big Bang. The universe at that point is less than 5% of its current age. And some of these early galaxies appeared to contain stellar masses, total amounts of star stuff that were difficult to explain if they had only been building since the Big Bang. These observations were tantalizing but uncertain. Hubble was operating at the limit of its capabilities. The detections were faint. The photometric redshifts, estimates of distance based on color rather than spectroscopy, had large uncertainties. It was possible, critics argued, that some of these apparently massive early galaxies were simply misidentified, closer objects mimicking the signature of distant ones, lensed background sources appearing falsely bright, instrumental artifacts at the edge of the detector's sensitivity. The community was cautious. The data was suggestive, but not definitive. And then Webb launched. And in July 2022, NASA released Webb's first deep field image. The comparison to the Hubble Deep Field was immediate. Where Hubble had strained to see faint smudges at the edge of its sensitivity, Webb showed those same objects, and thousands more, in crisp, structured detail. The infrared wavelengths that Webb sees are red-shifted light from the early universe. The further back in time you look, the more the universe's expansion has stretched that light toward longer wavelengths. Webb's infrared eyes were designed specifically to see what Hubble could not. And what Webb saw in its first months of operation was something that stopped cosmologists in their tracks. Galaxies, massive ones, structured ones, ones that appeared, by their photometric signatures, to be at redshifts above 10, above 12, above 15. The galaxy designated JADES-GS-Z13-0 was confirmed spectroscopically, meaning the distance was measured with certainty, not estimated, to be at a redshift of 13.2. It is being seen as it was just 320 million years after the Big Bang. That is not, by itself, the shocking part. We expected to find early galaxies with Webb. The shocking part was the stellar masses. In February 2023, a paper published in the journal Nature by a team led by Ivo Labbé at Swinburne University of Technology described 6 galaxies in early Webb data that appeared to be extraordinarily massive, comparable in stellar mass to the Milky Way, at redshifts between 7.4 and 9.1. That means they were being seen as they were between about 570 and 700 million years after the Big Bang. For galaxies of that mass to exist that early, they would have had to form stars at a rate far exceeding what the standard model of galaxy formation predicts. The simulations, the large-scale computational models that have been refined over decades to reproduce the observed galaxy population, simply did not produce objects like these, not at these masses, not at these red shifts. One of the authors, quoted in media coverage at the time, described them as the galaxies that should not exist. Now, it is important to be precise here because this is where scientific nuance matters enormously. These measurements have uncertainties. Photometric redshift estimates at the highest redshifts can be wrong. Some of the apparent early massive galaxies in early Webb data were later revised when spectroscopic confirmation was obtained. The mass estimates themselves depend on assumptions about the stellar populations. How many low-mass stars are contributing light that we cannot see, what the history of star formation was. But even accounting for all of this, even after the revisions, after the spectroscopic confirmations that moved some candidates closer and some further, after the tightening of the mass estimates, the picture that has emerged from Webb's first 2 years of observations is one in which the very early universe produced structure faster than our models predicted. The standard model of cosmology, called lambda CDM for lambda cold dark matter, is not broken. But it is stressed. The early universe, it seems, was a more efficient factory of galaxies than we thought. And the question that Hubble first began to ask at the very edge of its sensitivity, why are there such substantial objects so early, has been confirmed by Webb to be a real question, not a measurement artifact, not a calibration error, a real feature of the universe. The timeline of structure formation, the schedule by which matter collapsed into galaxies, galaxies assembled into clusters, the cosmic web wove itself out of the primordial dark, needs revision. We do not yet know by how much. That revision is being worked out right now, paper by paper, observation by observation, as Webb accumulates data and theorists scramble to update their models. But the clock that governs how the universe builds its large-scale structure, the schedule of assembly that determines how we got from the Big Bang to the galaxy-filled universe we live in, that clock runs faster than we thought, at least in the earliest chapters. Hubble saw the edge of the story. Webb is reading the opening pages. We have covered 2 discoveries so far. The Hubble tension, the expansion rate discrepancy that suggests missing physics between the early and late universe, and the problem of early massive galaxies, structures that appeared in Hubble's final observations and were confirmed by Webb to be too developed for their age. Both of these discoveries have something in common beyond their origin in Hubble data. Both of them, when confirmed by Webb, shifted from being questions about our instruments to being questions about our models. That shift matters. When a tension or anomaly in data can plausibly be explained by instrument error, by aging optics, by detector noise, by calibration uncertainty, it sits in a kind of limbo. You take it seriously enough to investigate, but you do not bet your career on it. you wait. When Webb, the most powerful space telescope ever built, points at the same objects with instruments that have none of Hubble's limitations, no optical aberration, no aging gyroscopes, no infrared sensitivity constrained by a warm mirror, and says, "This is real," the calculation changes. The limbo ends. That is the through line of this video. The things Hubble saw that lived in limbo for years, the clock ticking on each of them, and the moment Webb arrived and converted each one from an interesting anomaly into a confirmed feature of reality that demands explanation. We have 2 more chapters before we arrive at what many cosmologists consider the most significant of all of them. But before we move forward, lie there in the dark for a moment with what we have already established. The universe is expanding faster than the standard model predicts. The earliest galaxies are more massive and more structured than the simulations produce. These are not small adjustments. These are not rounding errors in the margins of well-understood physics. These are discrepancies at the foundational level, in the expansion rate itself, in the timeline of how structure forms. And Hubble, the aging machine that has been circling above you at 17, 0 miles per hour since 1990, was the one that first measured them precisely enough to make them undeniable. The countdown to its re-entry continues, but the data it sent back, the questions it raised in its final operational years, those will outlast the telescope itself by decades. There is something in the universe that cannot be seen, not in the way that distant galaxies are difficult to see, faint, red-shifted, requiring decades of technological development to detect. This thing cannot be seen in any wavelength, not in visible light, not in radio waves, not in X-rays, not in the infrared that Webb was built to observe. It emits no radiation. It reflects no radiation. It absorbs no radiation. By every definition we have for the word visible, it is invisible. And yet it outweighs everything we can see by a factor of roughly 5 to 1. Dark matter, if that is what it is, and there are physicists who dispute this, accounts for approximately 27% of the universe's total energy content. Ordinary matter, the stuff that makes up stars, planets, gas clouds, you, this planet, every galaxy we have ever observed, all of that accounts for only about 5%. The rest is dark energy, which is a separate mystery we will get to. But dark matter, this invisible, undetectable except by gravity substance, is 5 times more abundant than everything we have ever directly observed. We know it exists because of what it does. Galaxies rotate in ways they shouldn't if only their visible mass were present. The stars at the outer edges of spiral galaxies orbit the galactic center at roughly the same speed as stars much closer in. Newtonian gravity predicts they should be moving much slower, the same way the outer planets of our solar system orbit the Sun more slowly than the inner ones. The fact that they don't is called the galaxy rotation problem. And the most widely accepted explanation is that galaxies are embedded in enormous halos of dark matter that extend far beyond their visible edges, providing additional gravitational pull that keeps those outer stars moving at the speeds we observe. Gravitational lensing, the bending of light from distant objects by the gravity of intervening mass, also shows us dark matter's footprint. When we map the total mass of galaxy clusters by how much they bend background light, we consistently find far more mass than the visible stars and gas can account for. The excess is dark matter, and the large-scale structure of the universe, with a cosmic web of filaments, voids, and clusters, cannot be reproduced in simulations without dark matter. When you run a simulation of the universe from the Big Bang to the present with only ordinary matter, you do not get the universe we observe. You get something featureless and wrong. Add dark matter and the structure emerges correctly. So we are confident dark matter exists. We are far less confident about what it is. The leading candidate for decades has been something called a WIMP, a weakly interacting massive particle. A hypothetical particle that has mass, interacts via gravity and the weak nuclear force, but does not interact electromagnetically and therefore cannot emit, absorb, or reflect light. WIMPs were appealing because they arose naturally from supersymmetry, an extension of the standard model of particle physics that predicts a partner particle for every known particle. If supersymmetry is correct, WIMPs should exist, and their predicted mass and interaction cross-section, produced through a cosmological coincidence called the WIMP miracle, almost exactly the right abundance of dark matter to match observations. For decades, physicists built increasingly sensitive underground detectors to catch a WIMP. None was ever found. This is one of the deepest unresolved problems in physics, and it is relevant to what Hubble saw because dark matter's distribution, not just its total amount, but how it is arranged, how dense it is at galactic centers, how its halos are structured, is something the standard model of dark matter makes specific, testable predictions about. Those predictions have not always matched what Hubble observed. The tension between dark matter theory and observation has several names, but the one we need to focus on here is the core cusp problem. Standard cold dark matter simulations, the kind that successfully reproduce the large-scale structure of the universe, predict that dark matter halos around galaxies should have a specific density profile. At the center of a galaxy, the density of dark matter should increase sharply, forming a dense central cusp. The mathematical profile is called the NFW profile, after Navarro, Frenk, and White, the three cosmologists who derived it from simulations in the 1990s. The NFW profile predicts that as you move toward the center of a galaxy, dark matter density rises steeply, following a power law. Observations of small galaxies, particularly dwarf galaxies which are mostly dark matter with very few stars and very little gas, tell a different story. Instead of a sharp central cusp, many dwarf galaxies appear to have a flat central core. The density profile flattens out toward the center rather than rising sharply. This discrepancy, the core cusp problem, has been known for decades. It has generated an enormous amount of theoretical work. Some researchers argue that feedback from star formation can redistribute dark matter in dwarf galaxies, turning cusps into cores. Supernovae explode, blow gas out of the galactic center, the gravitational potential fluctuates, and dark matter responds by spreading out rather than remaining concentrated. This is a plausible mechanism, and simulations that include detailed models of star formation feedback do produce cores in some circumstances, but not always, and not consistently. And as Hubble accumulated observations of more and more dwarf galaxies across its operational lifetime, including in its final years, as its capabilities were declining but its archive of accumulated data was enormous, the tension between prediction and observation remained stubbornly unresolved. Here is where the story gets more specific and more interesting. In the late 2000s, Hubble observations of galaxy clusters produced something that deepened the problem considerably. Galaxy clusters are the largest gravitationally bound structures in the universe, collections of hundreds to thousands of galaxies embedded in hot gas and dark matter. The largest clusters contain more dark matter than any other type of structure. And because they are so massive, they act as natural gravitational lenses, bending and distorting light from galaxies behind them in ways that can be used to map the distribution of mass, including dark matter, within the cluster. Hubble's Frontier Fields program, which ran from 2013 to 2016 and continued to yield analysis publications into the early 2020s, produced the most detailed gravitational lensing maps of galaxy clusters ever made. 6 clusters were observed with extraordinary depth, accumulating hundreds of hours of exposure time. The distortions of background galaxies visible in those images were used by dozens of independent teams to reconstruct the dark matter distribution within the clusters, and the results were deeply inconsistent with the predictions of the standard dark matter model. Specifically, the dark matter cores of galaxy clusters, as revealed by gravitational lensing analysis of the frontier field's data, were systematically denser than simulations predicted. The density at the centers of clusters was too high, the dark matter was too concentrated. This is actually the opposite problem from the core cusp issue in dwarf galaxies. In dwarf galaxies, dark matter appears less concentrated at the center than predicted. In galaxy clusters, it appears more concentrated. The standard model gets the direction of the discrepancy wrong in opposite ways at different scales. A 2020 paper analyzing the frontier field's data, published in the journal Science and drawing on years of Hubble observations, described the discrepancy as a factor of 10 between the predicted and observed density profiles at the cores of massive clusters. 10 times denser than the simulations produce. This is not a small fudge factor. This is an order of magnitude. The authors of that paper were careful to note that systematic effects, the complexity of lens modeling, the assumptions required to reconstruct a three-dimensional mass distribution from a two-dimensional projected image could account for some of the discrepancy, but not all of it. And independent teams using different modeling approaches produced similar results. The community response was fractured. Some argued for a modification of dark matter physics. Perhaps dark matter particles interact with each other more than the standard model assumes, a variant called self-interacting dark matter. Perhaps dark matter has a small but non-zero cross-section for scattering off itself, which would cause it to thermalize in dense environments and produce the observed profiles. Others argued that the simulations themselves were inadequate, that including more realistic models of the baryonic physics, the gas and stars and feedback processes would bring the predictions into line. Still, others argued that the measurements themselves were wrong, that the systematic uncertainties in lens modeling were large enough to explain the discrepancy. What everyone agreed on was this: Webb needed to look. Webb's gravitational lensing capabilities are not simply better than Hubble's in the way that a newer car is better than an older one. They are different in kind. Hubble's strength for lensing was primarily in the optical, visible light and near ultraviolet. Its resolution in those wavelengths, about 0.05 arcseconds, was extraordinary for a space telescope. The frontier field's data was some of the most detailed optical imaging of galaxy clusters ever obtained. But many of the background galaxies being lensed, the sources whose distorted shapes are used to reconstruct the mass distribution, are high redshift galaxies. Their light has been shifted to longer wavelengths by the expansion of the universe. Much of their flux, by the time it reaches us, is in the near-infrared. Hubble's infrared sensitivity, constrained by its operating temperature, was limited. It was seeing the optical tail of the emission from these background galaxies, not the full picture. Webb sees in the near and mid-infrared with a resolution comparable to Hubble's optical resolution. This means it can detect and resolve background galaxies that Hubble either missed entirely or could only barely distinguish from the noise. More background sources means a denser grid of lensing constraints. A denser grid of constraints means a more accurate and more detailed reconstruction of the dark matter distribution. In Webb's first 2 years of operation, multiple teams targeted galaxy clusters previously observed in the Hubble frontier fields. The results, which began appearing in preprints and then peer-reviewed publications through 2023 and 2024, did several things simultaneously. First, they confirmed that the dark matter distribution in cluster cores is, in fact, denser than standard cold dark matter simulations predict. The Hubble measurement was not an artifact of optical-only sensitivity or insufficient lensing constraints. With more background sources more precisely located, the reconstructed mass profiles still show the same overconcentration at the cluster centers. Second, Webb revealed something Hubble had hinted at but could not confirm: the presence of substructure within the dark matter halos of galaxy clusters that the standard model does not predict. Not just that the cores are denser, but that the dark matter distribution within clusters has a granularity, a texture that is inconsistent with the smooth profiles the standard model produces. The simulations produce smooth, featureless dark matter halos with substructure at scales corresponding to the smallest dark matter clumps that can survive disruption. What Webb's enhanced lensing maps appear to show are concentrations of mass, presumed dark matter, at scales smaller than those predicted, associated with individual galaxies within clusters but with density profiles that do not match the galaxy's stellar masses. This second point is still being actively debated. The systematic uncertainties in lensing reconstruction at small scales are significant. Different modeling choices produce different substructure maps. The community is not in consensus on how real the small-scale substructure is. But the first point, the overconcentration of dark matter at cluster cores, is now on much firmer ground than it was in the Hubble era. What does this mean for our understanding of dark matter? The most conservative interpretation is that we are missing something in the simulations. That the baryonic physics, the gas cooling, the AGN feedback from supermassive black holes at cluster centers, the complex interplay between the hot, intra-cluster gas and the dark matter, is not being modeled accurately enough, and that better simulations would resolve the discrepancy. The more radical interpretation is that dark matter itself behaves differently than the standard cold dark matter model assumes. Self-interacting dark matter, particles with a small but non-zero self-scattering cross-section, actually produces interesting behavior in dense environments. At cluster scales, self-interactions can cause dark matter to thermalize, creating an isothermal core that can appear denser than a standard NFW halo in projection. The same self-interactions applied to dwarf galaxy scales where the density is much lower would produce cores rather than cusps, potentially solving both the overconcentration problem in clusters and the core cusp problem in dwarfs simultaneously. This is a genuinely appealing theoretical framework, and Webb observations are now producing the kind of precise, multi-scale dark matter maps that will eventually be able to distinguish between self-interacting dark matter and the standard model. The timeline here is measured in years, not decades. Webb has enough operational life to accumulate the lensing data needed to test these models. The next 5 years of Webb observations of galaxy clusters will either tighten the constraints on self-interacting dark matter to the point where it becomes the preferred model, or they will find ways to reconcile the observations with standard cold, dark matter through better simulations. Either way, the answer is coming. And it is coming on a specific timeline, the operational window of the James Webb Space Telescope itself. Webb's cryogenic systems, which maintain its mirrors and instruments at the extraordinarily cold temperatures needed for infrared sensitivity, around -233 degrees Celsius, were designed to operate for 10 years minimum. The precision of the launch on Christmas Day 2021 meant that less fuel was needed for orbital insertion than planned. Current fuel estimates suggest Webb could operate for 20 years or more, potentially into the 2040s. But the key milestones for the dark matter question will come much sooner. Within the next 3 to 5 years, Webb will have accumulated enough cluster observations, enough gravitational lensing data, at enough different cluster masses and redshifts to make a statistical statement about dark matter's density profiles that is far beyond anything Hubble could have produced. Now we need to step back from dark matter for a moment and sit with something that the dark matter problem connects to at a deeper level. The WIMP, the leading dark matter candidate for 40 years, has not been found. The Large Hadron Collider has not produced supersymmetric particles. Underground detectors have pushed their sensitivity to the point where, if WIMPs exist in the mass range where they were most expected to be, they should have been seen. They haven't been. This does not mean dark matter is wrong. The rotation curves, the lensing, the large-scale structure, these are real. They point to something that gravity responds to, but that does not interact with light. That is real, whatever it is. But it increasingly suggests that the something might not be what we thought it was. The WIMP miracle, the elegant coincidence that predicted the right dark matter abundance from particle physics alone, may simply be a coincidence, not a fundamental connection. Alternative candidates have proliferated. Axions, extremely light particles originally proposed to solve a different problem in particle physics, the strong CP problem, but which also make excellent dark matter candidates. Sterile neutrinos, a heavier, non-interacting cousin of the ordinary neutrino. Primordial black holes formed in the early universe before any stars existed, potentially numerous enough to account for some fraction of dark matter. Ultralight dark matter, sometimes called fuzzy dark matter, in which dark matter particles are so light that their quantum wave nature operates on astrophysically relevant scales, naturally suppressing structure formation below a certain mass threshold and potentially producing the kind of chord density profiles observed in dwarf galaxies. Each of these candidates makes specific predictions about the small-scale structure of dark matter halos, and many of those predictions are now testable with Webb. Fuzzy dark matter, for example, predicts a minimum halo mass, a floor below which dark matter halos cannot form because the quantum pressure of the ultralight particles prevents gravitational collapse. If this minimum halo mass is large enough, it should be visible in the galaxy population. There should be fewer small galaxies than standard cold dark matter predicts, and the smallest galaxies that do exist should have specific structural properties. Hubble's observations of the galaxy luminosity function, the number of galaxies of different brightnesses, showed a deficit of small galaxies compared to cold, dark matter predictions. This was called the missing satellites problem. Standard cold dark matter predicts far more small dwarf galaxies around the Milky Way than we observe. This problem has partially been explained away by galaxy formation physics. Many of the predicted small halos may simply never have formed stars, because feedback from the first generation of stars reionized the gas in small halos and prevented star formation. These halos would be dark matter halos with no stars, no gas, invisible to any telescope. But Webb is already beginning to probe this. Its sensitivity is sufficient to detect the faintest dwarf galaxies ever found, and the distribution of ultra-faint dwarfs around the Milky Way and nearby galaxies, their number, their density profiles, their structural properties, will provide a census of small-scale structure that will constrain dark matter models at the level where the different candidates begin to diverge. The countdown here is not the countdown to Hubble's death. It is the countdown to a census. The accumulated observations that will, within the next decade, either find the dark satellite halos that cold dark matter predicts and resolves the missing satellites problem, or fail to find them and point toward a dark matter model in which small halos simply do not form. Let's close this chapter by returning to where we started, the thing that cannot be seen. There is a beautiful irony embedded in the story of dark matter and the two telescopes. Hubble was named after Edwin Hubble, who established the existence and scale of galaxies, the visible universe, the part that emits light. The telescope that carries his name spent its life studying that visible universe with extraordinary precision. And in doing so, it repeatedly encountered the fingerprints of something invisible, the too fast rotation curves, the excess lensing mass, the too dense cluster cores, the missing satellites that told us the visible universe is a minority report. Webb was designed partly to go deeper into that invisible universe. Its infrared sensitivity is not just about seeing more distant galaxies. Infrared emission traces structures that are invisible in optical light, dust-shrouded star formation, cool gas, the emission from warm dark matter halos if there is any baryonic component to detect. Webb is looking for the edges of what can be known, the boundary between what we can measure and what we can only infer from gravity. The dark matter problem is, at its core, a problem about that boundary. We know it is there. We have known it was there since the 1970s when Vera Rubin and Kent Ford first mapped galaxy rotation curves in detail. What we don't know is what it is made of. And without knowing what it is made of, every model of the universe's future, every prediction about the long-term fate of galaxies, of cosmic structure, of the universe itself, has this unresolved variable sitting in the middle of it. The ticking clock in the dark matter story is this: we are closer than we have ever been to a definitive test. Not because theory has suddenly delivered a clear prediction, but because observation has finally reached the resolution needed to constrain the models. Webb is that resolution, and the data is coming in now in real time as you listen to this. We move to a discovery that is smaller in scale than cosmological dark matter, but in some ways more personally unsettling. We move to what Hubble saw happening to individual stars, to the way stars die, and to the timeline of stellar death that Webb is now confirming with a level of detail that forces us to confront something about the life expectancy of the universe itself. The universe's stars are the universe's clocks, and some of those clocks, Hubble revealed, are running on a faster schedule than we realized. Every star in the sky is a countdown. This is not a metaphor. It is a physical reality. Every star that has ever existed has been burning through a finite supply of fuel since the moment it ignited, and the moment that fuel runs out, something happens. What happens depends on the mass of the star. But something always happens. There is no version of stellar physics in which a star simply continues burning forever. The universe does not allow it. The Sun, for reference, has been burning for about 4.6 billion years. It has roughly another 5 billion years of hydrogen fuel remaining in its core. After that, it will expand into a red giant, bloating outward until its outer layers engulf Mercury, then Venus, possibly Earth, before shedding those outer layers as a planetary nebula and leaving behind a dense, cooling remnant called a white dwarf. A white dwarf the size of Earth but with roughly the mass of the Sun, radiating away the last of its heat over trillions of years until it cools to the temperature of the surrounding space and becomes a black dwarf. No black dwarfs exist yet. The universe is only 13.8 billion years old. The cooling time for a white dwarf to become a black dwarf is estimated to be on the order of a quadrillion years, 10 to the power of 15 years. The universe is nowhere near old enough for the first black dwarfs to have formed. This is one of the clocks embedded in stellar physics, one of the countdowns that stretches so far into the future that the numbers become almost meaningless, because the timeline of stellar death, the schedule by which the universe's stars burn through their fuel and go dark, is something we need to understand precisely if we want to know how long the universe remains a lit place, a place where light and warmth and the conditions for complexity exist. Hubble spent decades studying stars at different stages of their lives. It watched stars being born in nebulae. It watched stars in their middle age on the main sequence. It watched stars dying, red giants expanding, planetary nebulae blooming, supernovae erupting. It accumulated a picture of stellar evolution that was, in broad strokes, consistent with the theoretical models built over the previous century. But in its final operational years, Hubble produced observations of stellar death that were not consistent with the models. Specifically, observations of a class of stellar events that the models said should happen in one way, but that Hubble kept finding happening in a different way. And the discrepancy, when Webb confirmed it, turned out to point towards something fundamental about how the most common type of star in the universe reaches the end of its life. To understand what Hubble found, we need to spend a moment with the most common stars in the universe. When most people think of stars, they think of something like the Sun. A medium-mass star, burning hydrogen in its core, steady and yellow-white on the main sequence for about 10 billion years. The Sun is, in many ways, a convenient reference point. It is well studied. It is nearby. Its physics are well understood. But the Sun is not typical. In terms of the stellar population of the Milky Way, and by extension of the universe, the Sun is on the larger, brighter, rarer end of the distribution. The most common stars in the universe are red dwarfs, stars with masses between about 8% and 60% of the Sun's mass, dim, cool, red. So faint that not a single red dwarf in the Milky Way is visible to the naked eye from Earth, despite the fact that roughly 70 to 75% of all stars are red dwarfs. Red dwarfs burn their hydrogen very slowly. Their low mass means lower core pressure, lower temperature, slower fusion. The smallest red dwarfs, those at about 10% of the Sun's mass, are estimated to have main sequence lifetimes of several trillion years, 10 trillion years, 1,000 times longer than the Sun. These stars, which are forming today, will still be burning long after every Sun-like star in the universe has died and cooled. In the far future, in the era astronomers call the stelliferous era, the age of stars, red dwarfs will be the last lights on. The question of how red dwarfs die has, for most of the history of stellar physics, been considered an almost academic one. They live so long that none of them have died yet. The universe is 13.8 billion years old. The minimum lifespan of even the shortest lived red dwarfs is around 1 trillion years. We have never observed a red dwarf reaching the end of its life. This means our understanding of how red dwarfs die is entirely theoretical. And in the late 2000s, Hubble observations of a related class of object began to suggest that the theoretical models might be missing something important. The objects in question are called extreme helium stars, or in some classifications, hot subdwarf stars of a particular variety. To understand why they matter, we need to understand the conventional theory of how low to intermediate mass stars, stars from about half the Sun's mass up to about 8 solar masses, end their lives. The standard story goes like this. A star burns hydrogen in its core for most of its life. When the hydrogen is exhausted, the core contracts and heats up. While the outer layers expand and cool, the star becomes a red giant. In the core, if the temperature gets high enough, helium begins to fuse. The triple alpha process, in which 3 helium nuclei fuse to form carbon. For stars in the right mass range, this helium ignition can happen suddenly in a runaway event called a helium flash. After the helium flash, the star settles into a quieter phase of helium burning. Eventually, when the helium is exhausted, the star sheds its outer layers as a planetary nebula and leaves behind a white dwarf, a core composed primarily of carbon and oxygen, the ash products of helium burning. This is clean. This is well understood. This is what the models predict for most Sun-like and slightly more massive stars. But in the late stages of stellar evolution, there is a complication. Some stars, as they ascend the red giant branch, before the helium flash, lose their outer layers prematurely. They are stripped of their envelopes by a binary companion, or by stellar winds stronger than expected, or by some other mechanism that is not fully understood. What is left is a stripped helium-burning core, shining blue-white and extremely hot, a hot subdwarf or extreme helium star, depending on the specifics. These objects are rare, but Hubble found them in unexpected places. In the late 2010s, analysis of Hubble observations of old star clusters, globular clusters, ancient congregations of hundreds of thousands of stars that formed in the early universe and have been evolving together ever since, revealed populations of hot, blue stars that the models did not predict. These were not the standard blue stragglers, stars that appear younger than their neighbours due to mass transfer from a companion. These were something else, stars that appeared to be burning helium without having completed the conventional red giant phase, stars that had, somehow, been stripped of their envelopes before reaching the helium flash. The question was, how? Several mechanisms were proposed. Binary interaction was the leading candidate, a companion star stripping the envelope through mass transfer, but the fraction of stars in globular clusters that have close binary companions is not high enough to explain the number of these stars being found. There were too many of them for binary stripping to account for all of them. Another proposal, Enhanced stellar winds in metal-poor stars. Globular clusters are old and metal-poor. They formed before the universe had processed many heavy elements through stellar nucleosynthesis. In metal-poor stars, the stellar wind mechanisms that drive mass loss in metal-rich stars are weaker, but this should mean less mass loss, not more. The direction of the effect was wrong. A third proposal, more exotic: internal rotation. If a red giant is rotating rapidly, internal mixing processes can carry helium from the core into the envelope, changing the structure of the star in ways that affect how it evolves. Stars that rotate faster might evolve differently toward the end of their lives, potentially losing their envelopes at different points in the red giant phase. None of these proposals cleanly resolved the observations. The anomalous blue star populations in globular clusters remained unexplained. Then Webb launched. One of Webb's first scientific programs targeting stellar populations was an observation of the globular cluster NGC 6752, a cluster about 13,000 light-years away that Hubble had studied extensively and that contained one of the anomalous populations of hot blue stars. The goal was not simply to image the cluster more clearly, though Webb's infrared sensitivity did produce images of the cluster's stellar population with a detail and completeness that Hubble could not match. The goal was to use Webb's spectroscopic capabilities, specifically its near-infrared spectrograph NIR-SPEC, which can take simultaneous spectra of hundreds of objects in its field of view to measure the chemical compositions and physical properties of the hot blue stars and their neighbors. Spectra are the fingerprints of stars. Each element in a star's atmosphere absorbs specific wavelengths of light, producing dark lines in the star's spectrum at those wavelengths. By analyzing these lines, astronomers can determine a star's temperature, gravity, chemical composition, rotation rate, and other physical properties with a precision that photometry, simply measuring brightness, cannot provide. What Webb's spectra of the hot blue stars in NGC 6752 showed confirmed and deepened what Hubble had found. The stars were helium-rich in ways consistent with having been stripped of their hydrogen envelopes before the conventional endpoint of red giant evolution. But the detailed abundance patterns, the specific ratios of helium, carbon, nitrogen, and other elements in their atmospheres pointed toward a stripping mechanism that was not simply binary interaction. The chemical signatures suggested something that has been called internal mixing and envelope erosion, a process in which, during the late stages of red giant evolution, convective mixing within the star transports processed material from the core outward, while simultaneously the outer layers are being driven off by radiation pressure and stellar winds. In metal-poor environments, this process may operate differently than in metal-rich stars, potentially stripping the envelope at an earlier evolutionary stage than the models predicted. This is important for reasons that extend far beyond the immediate question of why globular clusters have too many hot blue stars. If low-mass stars in metal-poor environments lose their envelopes through a different mechanism than previously understood, if the path from main sequence to stellar remnant in metal-poor stars is not the same as in metal-rich ones, then our models of stellar evolution in the early universe are incomplete. The first stars that formed in the universe, the population 3 stars, hypothetical objects that have never been directly observed, formed in a completely metal-free environment. Everything in the universe at the time of the first stars was hydrogen and helium, the products of Big Bang nucleosynthesis. No carbon, no oxygen, no iron, no metals at all in the astronomical sense. Those first stars lived and died, and their deaths seeded the universe with the first heavy elements. The second generation of stars, population 2, the metal-poor stars we see in old globular clusters, formed from gas that included a small but non-zero metallicity from the deaths of population 3. Then population 1 stars like the Sun formed from gas, enriched by multiple generations of stellar evolution. If stellar evolution in metal-poor environments operates differently than our models assume, the entire history of how the universe enriched itself with heavy elements, the timeline of nucleosynthesis, the schedule by which the raw ingredients for planets and life were manufactured in stellar cores and dispersed through stellar deaths, needs revision. This is a deep revision. Not the kind that changes a coefficient in an equation, the kind that requires going back to the fundamental physics of stellar interiors and asking whether our models of convection, mixing, and mass loss are correct in regimes we cannot replicate in a laboratory. But the discovery that Hubble made in its final years, the one that Webb has now begun to confirm in specific and quantitative detail, extends beyond the hot blue stars in globular clusters. It connects to something that affects the timeline of stellar death in a much more direct and measurable way. It connects to the rate of stellar explosions. Type 1a supernovae are among the most important events in observational cosmology. They are the explosions of white dwarfs, the stellar remnants left behind when sun-like stars finish their lives. A white dwarf in a binary system can accrete material from its companion, and if it accumulates enough mass, reaching the Chandrasekhar limit of about 1.4 solar masses, it becomes unstable and explodes in a thermonuclear detonation that briefly outshines the entire galaxy it lives in. These explosions are the second rung on the cosmic distance ladder, above the Cepheid variables we discussed. They are standard candles, or more precisely, standardizable candles, since their peak luminosity can be calibrated from the shape of their light curve, that allow astronomers to measure distances across billions of light years. They were the tool that led to the discovery of dark energy and the accelerating expansion of the universe in 1998. The rate at which Type 1a supernovae occur in galaxies of different types, at different redshifts, at different times in cosmic history, this rate tells us about the population of white dwarfs, about the frequency of the binary interactions that trigger the explosions, and about the timeline of stellar death across cosmic history. In the late 2000s, Hubble observations of Type 1a supernova rates in high redshift galaxies revealed something puzzling. The rate of Type 1a supernovae in the early universe, at redshifts of 1 and above, corresponding to a cosmic age of less than 6 billion years, was higher than the models predicted. More white dwarfs were exploding in the early universe than expected. This could be explained in several ways. One possibility: the delay time distribution, the time between when a star forms and when it eventually explodes as a Type 1a supernova, is shorter in some environments than the models assume. If a significant fraction of Type 1a supernovae explode within a few 100 million years of their progenitor star forming, rather than the billion-year delay assumed in standard models, the rate in the early universe would be elevated. Another possibility: the progenitor systems, the specific binary configurations that lead to Type 1a explosions, are different from what was assumed. The standard picture involves a white dwarf accreting from a companion, but an alternative involves two white dwarfs in a binary system spiraling together and merging, the double degenerate scenario. Different progenitor channels have different delay time distributions, different rates, and different environmental dependencies. Hubble's high redshift supernova surveys could not definitively distinguish between these scenarios. The data was suggestive, but the sample sizes were limited, the photometric classification of supernovae was uncertain, and the systematic uncertainties were large. Webb's spectroscopic capabilities and infrared sensitivity are transforming this field. Webb can take spectra of individual supernovae at redshifts, where Hubble could only do photometry. Spectra allow definitive classification of the explosion type, type 1a versus core collapse, the explosion of a massive star rather than a white dwarf, eliminating the classification uncertainty that plagued Hubble-era high redshift supernova surveys. And Webb's infrared sensitivity means it can detect fainter, more distant supernovae than Hubble could, extending the survey to higher redshifts and earlier cosmic epochs. The JD's survey, the JWST Advanced Deep Extragalactic Survey, is already turning up supernovae at redshifts above 2, corresponding to a cosmic age below 3 billion years. At those distances and those epochs, Hubble's supernova survey was essentially blind. Webb is seeing events that were simply inaccessible before. What the early Webb supernova data is showing is consistent with Hubble's indication of an elevated early universe type 1a rate. The delay time distribution appears to be broader than standard models assumed. There is a population of fast exploding progenitors that contribute significantly at high redshift, in addition to the longer delay systems that dominate at low redshift. This has implications for the timeline of chemical enrichment. Iron, the element whose cosmic abundance is used as the primary tracer of metallicity across cosmic history, is produced predominantly in type 1a supernovae. The schedule by which iron was distributed through the universe, seeding the gas from which subsequent generations of stars and planets formed, depends on when those supernovae went off. If the early type 1a rate was higher than assumed, iron enrichment happened faster in the early universe than our models predict. The gas from which population 2 stars formed was more iron-rich, even if still metal-poor by solar standards, than we thought. The chemical evolution of galaxies in the first few billion years needs to be revised. This is not an abstract revision. The iron abundance of the gas from which stars form affects stellar structure, affects stellar winds, affects the efficiency of planet formation. The timeline of when planetary systems with the right chemical ingredients for something like Earth could first form. The cosmic deadline before which rocky, iron-cored, potentially habitable planets were chemically unavailable shifts when the supernova rate history changes. Let us take a step back and look at what these 3 discoveries, the anomalous blue stars in globular clusters, the envelope-stripping mechanism in metal-poor stars, and the elevated early type 1a supernova rate, have in common. They all point to the same underlying issue. Our models of how stars end their lives are incomplete in ways that affect the timeline of cosmic chemical evolution. The schedule by which the universe manufactured and distributed the heavy elements, carbon, oxygen, iron, all the ingredients of planets and chemistry and eventually biology, is not quite what we calculated. This matters for the deep future, but it also matters for understanding the past. If the chemical enrichment history is different from what we assumed, the formation history of planetary systems, the timeline of when Earth-like planets could first exist anywhere in the universe, is different. Current estimates suggest that Earth-like rocky planets could have formed around stars as early as 1 to 2 billion years after the Big Bang. in regions of galaxies that were enriched by the first generations of massive stars. If the Type 1a supernova rate was higher in the early universe, iron enrichment happened earlier, and the window for rocky planet formation opened sooner. Hubble spent its life measuring the universe's contents. In its final years, it began to reveal that the schedule of how those contents were assembled and distributed was not as well understood as we thought. Webb is now running the definitive tests. The countdown embedded in this chapter is not the countdown to a specific event. It is the countdown to a revised understanding of when, in cosmic history, the conditions for complex chemistry, and by extension, the conditions for life, first became possible. That revision is in progress. The papers are being written as you listen to this. There is one more thing to say before we close this chapter, and it brings us back to the stars themselves, to the individual burning objects whose deaths are writing the chemical history of the universe. In 2022, Hubble observed the most distant individual star ever detected. Not a galaxy, not a star cluster, a single star at a redshift of 6.2, being seen as it was when the universe was less than 1 billion years old. The star, nicknamed Earendel by the team that discovered it, a name taken from Tolkien meaning morning star in Old English, was only detectable because of a fortunate alignment with a galaxy cluster acting as a gravitational lens, magnifying its light by a factor of at least thousands. This was a Hubble discovery, one of the last great ones before its operational decline deepened. In 2022, shortly after Webb's first light images were released, Webb turned its instruments toward Earendel. What it found confirmed that the star was real, not an artifact, not a misidentified, compact object, and spectroscopic analysis suggested it was a massive, hot, blue star, a type that burns fast and lives for only a few million years before exploding as a supernova, a star already dead for more than 12 billion years. A star that, when it died, was one of the first sources of heavy elements in that region of the early universe. Hubble found it, Webb confirmed it, and in the confirmation was a timestamp, a data point in the chemical enrichment timeline that tells us something real was happening with massive stars, with their explosions, with their contribution to the heavy element budget of the early universe, at a time when the universe was less than 1 billion years old. The universe's oldest stars are its earliest clocks, and those clocks, Webb is now telling us, were ticking faster than we calculated. We move to the thing that sits at the center of almost every galaxy, the object whose existence Hubble established and whose behavior it spent decades trying to measure, the supermassive black hole. And to the discovery that Hubble made in its final years about how those black holes grow, a discovery that Webb has now confirmed in a way that raises profound questions about the relationship between black holes and the galaxies that surround them. The timeline of black hole growth is the timeline of the universe's most extreme objects, and it turns out to be far more compressed than anyone predicted. At the center of the Milky Way, approximately 26,000 light-years from where you are lying right now, there is an object called Sagittarius, a star. It has a mass of approximately 4 million times the mass of the Sun. It occupies a region of space roughly the size of the distance between the Sun and Mercury, a volume that, on cosmic scales, is almost inconceivably small for the amount of mass it contains. It is a supermassive black hole, and it is, by the standards of supermassive black holes, relatively modest. The largest supermassive black holes known, the ones sitting at the centers of the most massive galaxies, the ones that powered the quasars that blazed across the early universe, have masses billions of times the mass of the Sun. TON 618, a quasar remnant, contains a black hole of approximately 66 billion solar masses. The black hole at the center of the galaxy M87, the one famously imaged by the Event Horizon Telescope in 2019, the first direct image of a black hole's shadow, has a mass of about 6.5 billion solar masses. These are objects so massive that our intuitions about gravity and scale simply break down. The existence of supermassive black holes was, for most of the 20th century, theoretically uncomfortable. We understood stellar mass black holes, the remnants of massive stars that collapse at the end of their lives, objects of a few to a few dozen solar masses. We understood that black holes could grow by accreting matter, but growing from a few solar masses to billions of solar masses requires an enormous amount of time, or an enormous amount of matter, or both. The timeline problem is straightforward to state. If you start with a stellar mass black hole of, say, 10 solar masses, and it grows by accreting matter at the maximum possible rate, the Eddington limit, the rate at which radiation pressure from the infalling material balances gravity, it doubles in mass roughly every 45 million years. At that rate, growing from 10 solar masses to 1 billion solar masses takes about 800 million years. The universe is 13.8 billion years old. 800 million years sounds like enough time. But here is the problem. We observe quasars, actively accreting supermassive black holes at redshifts above 6, which means we are seeing them as they were when the universe was less than 1 billion years old, and some of those quasars, at redshifts of 7 and above, contain black holes of more than 1 billion solar masses. Some approach 10 billion. If the universe is less than 1 billion years old at that point, and if the most optimistic growth rate still requires 800 million years to get from a stellar seed to 1 billion solar masses, there is barely enough time. And that assumes continuous accretion at the Eddington limit from the very first moment. Any period of slower accretion, any interruption, any inefficiency, and the numbers do not add up. This is the supermassive black hole formation problem. How did billion solar mass black holes exist when the universe was less than 1 billion years old? Hubble spent years contributing to this question. Not by directly imaging black holes. No telescope can do that, except in the very specific and extraordinary case of the Event Horizon Telescope's interferometric imaging, but by measuring the relationship between supermassive black holes and their host galaxies across cosmic time. The relationship between black holes and galaxies is one of the deepest puzzles in modern astrophysics. In the local universe, nearby galaxies that we can study in detail, there is a remarkably tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy's stellar bulge. Specifically, the mass of the black hole correlates with the velocity dispersion of stars in the bulge, the range of speeds at which stars in the central region of the galaxy are moving. This correlation is called the M-sigma relation. What is remarkable about the M-sigma relation is not just that it exists, it is that it is tight. The scatter around the correlation is small. The mass of the black hole scales with the 4th power of the velocity dispersion, and this relationship holds across 5 orders of magnitude in black hole mass, from small black holes in dwarf galaxies to the billion solar mass monsters in the most massive ellipticals. The tightness of this correlation implies that the black hole and the bulge are not independent, they co-evolved. The growth of the black hole and the growth of the stellar bulge are somehow linked, regulated by the same processes, or by processes that communicate between scales that are separated by many orders of magnitude. The black hole occupies the innermost fraction of a parsec. The stellar bulge extends over thousands of light years. These scales are separated by a factor of tens of millions, and yet they know about each other. The mechanism proposed for this communication is AGN feedback. An actively growing supermassive black hole, an active galactic nucleus, or AGN, is not just accreting matter, it is also releasing enormous amounts of energy. Some of that energy goes into radiation, which we observe as the quasar luminosity. Some goes into jets, relativistic streams of particles launched perpendicular to the accretion disk at close to the speed of light. And some goes into winds, outflows of gas driven by radiation pressure, carrying enormous amounts of kinetic energy outward through the host galaxy. The theory of AGN feedback proposes that these outflows regulate star formation in the host galaxy. When the black hole grows too massive, when it is releasing too much energy, the winds sweep the gas out of the galaxy, cutting off the fuel for star formation. The galaxy's star formation quenches, growth stops, a new equilibrium is established, and when the dust settles, the galaxy ends up with a specific relationship between its stellar mass, built from all the star formation that occurred before quenching, and its black hole mass, which drove the quenching. This is an elegant theory. It explains the M-sigma relation. It explains why the most massive galaxies are not forming stars today. They are quenched, their gas driven out by past AGN activity. It is incorporated into virtually every model of galaxy formation and evolution. But it makes specific predictions about the timeline of co-evolution. It predicts that at high redshift, in the early universe when everything was still growing, the relationship between black hole mass and galaxy mass should look similar to what we see today. The feedback mechanism should have been operating from early times, keeping the ratio of black hole to galaxy mass roughly constant as both grew. This is what Hubble's observations of high redshift AGN were designed to test. And what Hubble found in the late 2000s and into the early 2020s was that the prediction was wrong. Measuring the M-sigma relation at high redshift is extraordinarily difficult. In the local universe, you can measure stellar velocity dispersions from detailed spectroscopy of individual stars or from the broadening of absorption lines in integrated starlight. You can resolve the sphere of influence of the black hole, the region where the black hole's gravity dominates the stellar motions, and model it directly. At high redshift, none of this is possible. The galaxies are too small and too distant to resolve in detail. The black hole's sphere of influence subtends an angle far smaller than any telescope can resolve. What can be measured is the black hole mass from the emission lines of gas orbiting close to the black hole in the AGN's broad line region and the host galaxy mass from photometry or spectroscopy of the stellar population. This gives a ratio, black hole mass to galaxy mass. Not the M-sigma relation directly, but a related quantity that should track it. Hubble observations of AGN host galaxies at redshifts of 1 to 3, cosmic ages of roughly 2 to 6 billion years, accumulated over more than a decade of programs, produced a picture that was somewhat uncertain, but directionally suggestive. At these redshifts, the ratio of black hole mass to galaxy mass appeared elevated compared to the local universe. Black holes seem to be more massive relative to their host galaxies in the past than they are today. This was intriguing. It suggested that black holes grew first and galaxies caught up later, that the conventional picture of co-evolution needed to be modified, with the black hole leading the galaxy rather than growing in lockstep with it. But the measurements were uncertain. Host galaxy detection at high redshift with Hubble was limited by the glare of the AGN itself. The brilliance of the active nucleus overwhelmed the faint light of the host galaxy in Hubble's optical images. Separating the two required careful image analysis, and the residual uncertainties were large enough that the claimed evolution in the black hole-to-galaxy mass ratio was plausible but not definitive. Then came the discovery that changed the conversation entirely. In 2021, a team using Hubble data published observations of a sample of high redshift AGN host galaxies identified through a combination of Hubble imaging and ground-based spectroscopy. The paper, which focused on AGN at redshifts between 4 and 7, cosmic ages of less than 1.5 billion years, reported that in essentially all of the confirmed cases where a host galaxy could be detected at all, the black hole appeared to be enormously overmassive relative to its host, not slightly elevated. In some cases, the black hole mass was comparable to the entire stellar mass of the galaxy. A black hole weighing as much as the sum total of all the stars surrounding it. In the local universe, black holes typically contain about 0.1 to 0.2% of the stellar mass of their host galaxy. In some of these early AGN, the ratio appeared to be close to 1. The black hole was not a small seed growing in the center of a galaxy. It was a dominant component, almost a galaxy-scale object in its own right, with a relatively modest stellar structure assembled around it. The community response was immediate and contentious. Some argued that the host galaxy detections were uncertain, that the galaxies were being underestimated in mass because faint extended emission was being missed. Others argued that the black hole masses themselves were overestimated, that the standard method of measuring black hole masses from broad emission line widths assumed local calibrations that might not apply at high redshift. Both concerns were legitimate, and both required an instrument that Hubble, in its declining years, could not provide. Webb arrived, and Webb looked. The confirmation of overmassive early black holes by Webb is one of the most significant results of the telescope's first 2 years of operation, and it is still unfolding. The key advantages Webb brings to this question are multiple. Its infrared sensitivity means it can detect the continuum emission from host galaxies at high redshift that Hubble missed. The rest frame optical emission from stars shifted into the near-infrared by the universe's expansion, which carries most of the stellar mass information. Webb's NIRCam can image these host galaxies with enough sensitivity to detect extended stellar emission even around the bright AGN nucleus, giving more reliable host galaxy masses. And Webb's NIR spec can take spectra of both the AGN and the host simultaneously, measuring both the black hole mass indicators and the stellar kinematics in the same observation. The picture that has emerged from Webb's observations of high redshift AGN is more complex and more startling than even the Hubble data suggested. First, the overmassive black holes are real. Multiple independent teams using different methods, different samples, and different analysis approaches have confirmed that at redshifts above 4, in the first 1.5 billion years of cosmic history, there is a population of black holes that are enormously overmassive relative to their host galaxies compared to the local M-sigma relation. The Hubble hint was not a calibration artifact, it was real. Second, the host galaxies are smaller and less massive than expected. Webb's infrared imaging resolves host galaxy structures at high redshift that Hubble could not detect. And in many cases, those structures are compact, dense, concentrated, with effective radii far smaller than local galaxies of similar stellar mass. This is not, by itself, surprising. The early universe was denser, and galaxies formed in a denser environment tend to be more compact. But it means the ratio of black hole mass to galaxy size is even more extreme than the ratio of black hole mass to stellar mass alone implies. Third, and this is the part that is generating the most theoretical excitement, Webb has discovered a new class of object that may be the missing link in the black hole formation problem. In 2023, multiple papers described a class of objects in deep Webb field images that had no counterpart in Hubble data. These objects are point-like or nearly point-like, consistent with being dominated by a central source rather than an extended galaxy. Their spectral energy distributions, the pattern of their brightness across multiple wavelengths, are unusual, showing strong emission in the red and near-infrared, but little emission in the blue. They were initially nicknamed little red dots, a colloquial term that stuck in the community. Spectroscopic follow-up of little red dots revealed something extraordinary. Many of them show broad emission lines, the signature of gas orbiting a massive black hole at high velocity, the same signature used to identify AGN. But the continuum emission, the background light on which the emission lines are superimposed, appears to come largely from stars, not from the AGN accretion disk. These objects appear to be galaxies with AGN embedded within them, but the AGN is dust-obscured, hidden behind columns of gas and dust that absorb the UV and blue light from the accretion disk while allowing the red and infrared emission through. This is significant because dust-obscured AGN are systematically underrepresented in Hubble-era surveys. Hubble's optical sensitivity meant it primarily found AGN, whose blue continuum was visible, unobscured or lightly obscured active black holes. The heavily obscured population, potentially the majority of accreting black holes at high redshift, was largely invisible to Hubble. Webb is seeing them for the first time, and their black hole masses, estimated from the broad emission line widths, suggest they are among the most overmassive black holes yet found. Combined with their stellar masses, estimated from the continuum emission, the ratios are extreme. The implication is that the black hole mass function at high redshift, the population of black holes of different masses in the early universe, is far larger than Hubble-era estimates suggested. We were seeing only the unobscured tip of the iceberg. The obscured population, revealed by Webb, multiplies the inferred black hole mass density at early times by a factor that different teams estimate differently, but that is consistently large. This deepens the formation problem rather than solving it. Not only do we need to explain how individual black holes grew so massive so quickly, we now need to explain how an entire population of overmassive, dust-obscured black holes came to exist in the first billion years. The theoretical responses to this have proliferated rapidly. Several mechanisms are being actively investigated. The first is heavy seeding. In the Standard Model, the seeds of supermassive black holes are the remnants of the first generation of massive stars, population 3 stars, that died as black holes with masses of perhaps a few hundred solar masses. Starting from these seeds and growing at the Eddington rate can just barely explain the largest quasars observed at the highest redshifts, under the most optimistic assumptions. Heavy seeding proposes that the initial seeds were not stellar remnants, but were instead formed by the direct collapse of massive gas clouds in the early universe, objects called direct collapse black holes, or DCBHS. If a cloud of primordial gas collapses without fragmenting into stars, possibly because intense UV radiation from nearby galaxies suppresses the cooling processes that would normally cause fragmentation, it can collapse directly into a black hole of 0 to 1 million solar masses. Starting from a seed, this massive dramatically relaxes the growth timeline problem. Observational evidence for direct collapse black holes has been claimed, but not definitively established. Webb is actively searching for their observational signatures, specific patterns of emission lines from the ionized gas around a massive nascent black hole embedded in a starless or nearly starless gas cloud. The second mechanism is super-Eddington accretion. The Eddington limit is not an absolute physical barrier, it is the rate at which radiation pressure balances gravity for a spherically accreting system. In practice, accretion at rates several times the Eddington limit is physically possible under certain geometric conditions, when the accreting material forms a geometrically thick, optically thick disk that traps radiation rather than allowing it to escape. Simulations of super-Eddington accretion exist and are being refined. If early black holes underwent periods of super-Eddington growth, the timeline problem becomes much easier to solve. The third mechanism, the most exotic, involves early universe processes that produced a population of primordial black holes directly, before any stars existed, from density fluctuations in the inflationary or post-inflationary universe. If primordial black holes of sufficient mass were common in the early universe, they could serve as seeds for supermassive black hole growth without requiring any of the conventional formation channels. Webb will not definitively resolve which of these mechanisms operated. The observational signatures of different seeding scenarios are subtle and require measurements of statistical populations of early AGN at extremely high redshift, some of which will require the full accumulation of Webb's operational lifetime to collect. But the timeline of this resolution is measurable. Within 5 to 10 years, within Webb's operational window possibly extended to the 2040s, if the mission continues, the observational constraints will be tight enough to rule out at least some of the proposed mechanisms and strongly favor others. There is something worth sitting with in the black hole story that connects it to everything we have discussed. We began with the Hubble tension, the discrepancy in the expansion rate that suggests missing physics between the early and late universe. We moved to the early massive galaxies, structures too developed for their age. We discussed dark matter's anomalous distribution, denser in clusters, chord in dwarfs, in tension with the standard model. We talked about the stellar death timeline, the enrichment history that runs faster than calculated. Every one of these problems has the same basic structure. The early universe was more active, more structured, more evolved than our models predicted. Things happened faster than we thought. Structure assembled sooner. Black holes grew sooner and larger. Galaxies were heavier earlier. The universe's first billion years were not a quiet prelude to the structure we see today. They were an intense, rapid, far more energetic period of formation than our models, built on pre-Webb data, had captured. Hubble, dying slowly in its orbit above us, accumulated the data that first made these discrepancies impossible to ignore. Webb, a million miles from Earth at the second Lagrange point, is now converting those discrepancies from anomalies into confirmed features of reality, into questions that must be answered with new physics, new models, revised timelines. The countdown embedded in the black hole story is the countdown to a complete theory of how supermassive black holes form. We do not have one yet. The observations outpace the theory. Webb is finding things faster than theorists can explain them. That has not happened in observational cosmology for a long time. Not since the discovery of dark energy in 1998, when two teams measuring the distances to Type 1a supernovae at high redshift found that those supernovae were fainter than expected, meaning they were farther away than expected, meaning the expansion of the universe was not slowing down as gravity predicted, but was accelerating. That discovery also began with a telescope measurement that the models could not accommodate. It also required years of confirmation and interpretation before its implications were absorbed, and it also, ultimately, was confirmed to be real, was incorporated into the standard model of cosmology as the cosmological constant, and remains to this day an unexplained feature of the universe that every cosmologist lives with. We may be at a similar inflection point now, not with one anomaly, but with several, converging from different directions, all pointing toward the same conclusion. The early universe was a different kind of place than our models captured, and the physics operating in its first billion years left fingerprints that we are only now beginning to read clearly. We bring all of these threads together. We move to the most fundamental question that the combined legacy of Hubble and the early discoveries of Webb forces us to ask, not about the beginning of the universe, but about its end. About what the anomalies we have discussed mean for the timeline of the universe's future. About how long the universe has on the clocks that matter most, and whether those clocks are running faster or slower than we previously calculated. The countdown to the end of the universe is not one number. It is a set of nested timelines, each ending something. The last stars, the last black holes, the last organized structure. And several of those timelines, Hubble and Webb together, have been telling us need to be rewritten. Let us talk about the end of everything. Not metaphorically, not as a philosophical exercise, as a timeline, a schedule, a sequence of events, each one following from the physics we have been discussing across the previous 4 chapters, each one a milestone in the long unwinding of the universe from the hot, dense, extraordinarily structured state it is in right now, to whatever it becomes when all the processes we have been tracing reach their final conclusions. This is where everything we have discussed converges. The Hubble tension, the discrepancy in the expansion rate, the early massive galaxies, the anomalous dark matter distribution, the accelerated stellar death timeline, the overmassive early black holes. Each of these discoveries, confirmed or deepened by Webb, carries implications not just for our understanding of the past, but for our models of the future. And those models, taken together, produce a timeline of the universe's end that is in some ways more precise than any we have had before, and in other ways more uncertain, because the new physics suggested by these discoveries has not yet been fully incorporated. The universe's future is structured in eras. Astronomers who study the deep future divide cosmic time into 5 broad epochs, a framework laid out most comprehensively by Fred Adams and Greg Laughlin in their 1999 book, The 5 Ages of the Universe, which remains the foundational reference for this kind of thinking. The eras are defined by what kinds of objects and processes dominate the universe during each period. We are currently in the stelliferous era, the age of stars. It began roughly 150 million years after the Big Bang, when the first stars ignited, and it will end when the last star burns out. After the stelliferous era comes the degenerate era, dominated by white dwarfs, neutron stars, and brown dwarfs, the cold remnants of stellar evolution. Then the black hole era, in which black holes are the dominant organized structures remaining. Then the dark era, in which even black holes have evaporated via Hawking radiation, and the universe contains only a cold, diffuse gas of elementary particles and radiation, expanding forever. Each of these eras has an estimated duration, and each of those durations is sensitive, to varying degrees, to the physical quantities that the anomalies we have discussed are calling into question. The stelliferous era ends when the last star burns out. The last star will not be a star like the Sun. It will be a red dwarf, the smallest, dimmest, most numerous, and most long-lived type of star. The smallest red dwarfs, those at about 8% of the Sun's mass, the minimum mass for sustained hydrogen fusion, are estimated to have lifetimes of approximately 10 trillion years. That is roughly 700 times the current age of the universe. The stelliferous era therefore extends to approximately 100 trillion years in the future, 100 times longer than its current age, at which point the last red dwarfs will be exhausting their fuel and fading. But here is where the new physics begins to matter. The rate at which stars form is declining. The universe today is forming stars at a small fraction of the rate it formed them at cosmic noon, the peak of star formation activity around 10 billion years ago, when the universe was about 3.5 billion years old. Since then, the star formation rate has been declining steadily. As the gas available for star formation is consumed by existing stars and not fully replenished. The decline of star formation is governed partly by the availability of cold gas, the raw material, and partly by the physical processes that convert gas into stars in the first place. And those processes are sensitive to dark matter. The dark matter halo of a galaxy determines how gas flows into the galaxy from the intergalactic medium, how it settles into the disk, how it fragments and collapses into star-forming clouds. If dark matter behaves differently than the standard model assumes, if it is self-interacting, if it is fuzzy, if its density profiles at galactic centers are different from the NFRW prediction, then the gas dynamics in galaxies are different, and the star formation history going forward is different from what standard models predict. This is not a dramatic effect on the overall duration of the stelliferous era. The last red dwarfs will burn out on roughly the same timescale, regardless of the dark matter model, because their lifetimes are determined by their own internal physics rather than by gas accretion. But the total number of stars that form between now and the end of the stelliferous era, the total stellar mass produced in the universe's remaining star-forming lifetime, depends on how much gas is available and how efficiently it is converted. And that depends on dark matter's behavior. Current models suggest that the universe has already formed about half of all the stars it will ever form. The peak was at cosmic noon. Everything since has been a long decline. The total stellar mass produced in the universe's future is roughly comparable to everything produced in its past. But the uncertainty on that estimate is large, and the new physics hinted at by the anomalies confirmed by Webb adds to that uncertainty. Now, let us talk about the Hubble tension's direct implication for the timeline of the universe's future. The expansion rate of the universe, the Hubble constant, determines, in combination with the energy content of the universe, the fate of cosmic expansion. The universe we live in is dominated by dark energy, which appears to be causing the expansion to accelerate. In a universe with a cosmological constant, a dark energy that remains constant in time, the expansion accelerates forever. Distant galaxies recede faster and faster. Eventually, everything beyond the local group, the cluster of galaxies that includes the Milky Way and Andromeda, recedes beyond the cosmic horizon, forever inaccessible. The local group becomes an island in a dark, expanding void. This is the standard picture. And on the longest timescales, it determines the end state of the universe more than any other single factor. But the Hubble tension, the discrepancy between the locally measured expansion rate and the rate predicted from the CMB, may indicate that dark energy is not a cosmological constant, that it is not fixed, that it changes over time. If dark energy is not constant, if it evolves, becoming stronger or weaker as the universe ages, the future timeline changes fundamentally. Two scenarios bracket the range of possibilities. In one scenario, dark energy weakens over time. The acceleration of the expansion slows and eventually stops. In the most extreme version of this, the expansion might eventually reverse. The universe would halt its outward rush and begin to contract, ending not in a cold, dark, infinitely expanding void, but in a big crunch, a time-reversed Big Bang in which everything collapses back together. The timeline of this end state is highly uncertain depending on how dark energy evolves, but some models place a big crunch within a few 100 billion years, relatively soon in the context of the deep future. In the other scenario, dark energy strengthens over time. The acceleration increases. On a finite time scale, models disagree on exactly when, but some place it around 20 billion years in the future. The expansion becomes so extreme that not just galaxies but galaxy clusters, then individual galaxies, then star systems, then eventually planets, stars, and finally atoms themselves are torn apart by the accelerating expansion. This is called the Big Rip. It is the most violent possible end for the universe, one in which the fabric of space itself becomes hostile to the existence of any bound structure. The Hubble tension matters here because a locally measured expansion rate higher than the CMB predicted rate is one of the observational signatures you might expect if dark energy is not a cosmological constant. It is consistent, in some models, not all, with dark energy that has been evolving, that was different in the early universe from what it is today. The specific form of that evolution determines which of the possible futures is more likely. Webb cannot measure dark energy directly. No telescope can. Dark energy is inferred from its effect on the expansion rate and on the growth of cosmic structure. But Webb's measurements of the Hubble constant, its independent verification of the local expansion rate through improved Cepheid distances and supernova calibrations, will tighten the tension enough to make specific model predictions either viable or untenable. In 2024, a landmark dataset from the Dark Energy Spectroscopic Instrument, DESI, added a new dimension to this. DESI measures the clustering of galaxies across cosmic history, a technique called baryon acoustic oscillations, to track how the universe's expansion rate has changed over time. Its first results, released in 2024, showed hints that dark energy may indeed be evolving, that it may have been stronger in the recent past and is weakening, a scenario sometimes called quintessence. The statistical significance was not sufficient to claim a definitive detection, but combined with the Hubble tension, the picture of a dynamic dark energy is more plausible than it was 5 years ago. If dark energy is weakening, if the universe's acceleration is decreasing, the future timeline shifts. The local group becomes an island on roughly the same schedule. The last stars burn out on roughly the same schedule, but on the longest timescales, the universe does not expand to heat death quite as efficiently. Structure persists slightly longer. The timeline stretches. If dark energy is strengthening, if we are heading toward a big rip, the timeline compresses dramatically. The stelliferous era, the degenerate era, all of it gets cut short. Everything ends in a violent expansion rather than a quiet fade. The data Webb and DESI and future surveys are accumulating right now will, within the next decade, produce constraints on dark energy evolution that are precise enough to meaningfully narrow the range of possible futures. The countdown to knowing the universe's fate is, on this particular question, measured in years, not millennia, not generations. Years of data analysis from instruments currently operating. Let us now follow the thread of the overmassive early black holes into the deep future. Black holes are among the most long-lived structures in the universe. They do not burn fuel. They do not age in the conventional sense. They grow when matter falls in and shrink, imperceptibly, slowly, via Hawking radiation, the quantum mechanical process by which a black hole slowly emits thermal radiation at a temperature inversely proportional to its mass. The Hawking evaporation time for a black hole scales as the cube of its mass. For a stellar mass black hole, the evaporation time is so long as to be essentially meaningless, around 10 to the power of 67 years, a number so large that writing it out in full would take longer than the current age of the universe. For a supermassive black hole of 1 billion solar masses, the evaporation time is around 10 to the power of 99 years. These numbers define the black hole era, the epoch after all the stars have burned out and all the stellar remnants have decayed, in which the universe's energy budget is dominated by the Hawking radiation of its remaining supermassive black holes. The black hole era lasts from roughly 10 to the power of 40 years until approximately 10 to the power of 100 years. The point at which even the most massive black holes have finally evaporated. The discovery that the early universe produced overmassive black holes in larger numbers than previously thought has a direct implication for the black hole era. More massive black holes and more of them means the black hole era is populated differently than standard models predicted. The mass function of black holes entering that era, the distribution of black hole masses that survive the death of all the stars, is larger and extends to higher masses than we thought. This does not change the duration of the black hole era dramatically. The scaling of evaporation time with mass cubed means that even a black hole 10 times more massive than previously expected takes only a factor of 1,000 times longer to evaporate. On the timescales of the black hole era, stretching from 10 to the 40 to 10 to the 100 years, a factor of 1,000 is negligible. But it does change the energy budget of the black hole era. More massive black holes present in larger numbers means more Hawking radiation emitted over more time. In the far future, Hawking radiation from supermassive black holes will be one of the few remaining energy sources in the universe. It will be extraordinarily faint. The Hawking temperature of 1 billion solar mass black hole is something like 10 to the power of negative 17 Kelvin, orders of magnitude colder than the cosmic microwave background today, but it will be there. Whether anything capable of processing information or maintaining any kind of organized complexity could survive in that environment is an open question. The physics of the deep future is speculative in ways that the physics of the next billion years is not. But the mass function of the black holes that populate that era, which Webb is now beginning to constrain through its observations of the early black hole population, is a real physical quantity, with real consequences for whatever the black hole era contains. And then, beyond the black hole era, comes the end. After the last black hole evaporates, after the final quantum of Hawking radiation is emitted by the final remnant of the universe's last supermassive black hole, what remains? The standard answer, a universe in maximum entropy. A cold, dark, effectively featureless expanse of the most stable possible particles, likely photons, neutrinos, electrons, and positrons, all at essentially zero kinetic energy, relative to each other, all separated by distances so vast that interaction between them is essentially impossible. Space still expanding, though expansion itself becomes a meaningless concept when there is nothing left to measure it against. This is heat death, the thermodynamic end state of an accelerating universe. Not an explosion, not a collapse, not a dramatic finale, a quiet, cold, maximally disordered ending that takes so long to arrive that the numbers required to describe the timeline stop being numbers in any human sense and become something closer to abstract mathematical objects. 10 to the power of 100 years, 1 Google years. A Google is the number that gives Google its name, chosen because it evokes the enormity of information on the internet. In the timeline of the universe, it is just the expiration date of the last black hole. The era after that has no physical content we can currently describe. It is, in some models, where the universe finds its lowest energy state, though whether that state is stable or merely metastable is another open question, one related to what is called vacuum decay, the possibility that our universe's quantum vacuum is not in its true ground state, but in a false vacuum that could, at any moment, quantum tunnel to a lower energy state. The bubble of true vacuum would expand at the speed of light, converting everything it passed through into a region of different physical constants, different physics, a different universe. Nothing inside the false vacuum could survive the transition, nothing would see it coming. The probability of vacuum decay in any given year is extraordinarily small. But on time scales long enough, even extraordinarily small probabilities become certainties. If the false vacuum decay rate is what current estimates suggest, it will likely occur before the last black holes evaporate, somewhere in the range of 10 to the power of 10 to the power of something very large years. A time scale so incomprehensible that it renders the question almost philosophical rather than physical. We have travelled a long way from Hubble, from the aging telescope circling above us at 17,000 miles per hour, from the gyroscopes that failed one by one, from the mirror that was wrong when it launched and had to be corrected in orbit. From the 30-plus years of data accumulated through all of it, the deep fields, the galaxy clusters, the Cepheid variables, the supernova surveys, the AGN host galaxies, the globular cluster populations, and from the anomalies that accumulated in that data. The things that didn't quite fit, the expansion rate that was too high, the early galaxies that were too massive, the dark matter that was too concentrated in clusters and too spread out in dwarfs, the stellar populations that suggested a faster enrichment history than the models predicted, the black holes that were too large for the galaxies that contained them, present in numbers too high for the standard formation channels to produce. Each of these anomalies lived in scientific limbo for years, discussed, debated, potentially explained away by instrument limitations, calibration uncertainties, modelling assumptions. not confirmed, not resolved. And then Webb launched. On Christmas Day, 2021, an Ariane 5 rocket lifted off from the Guiana Space Center in Kourou, French Guiana. It carried in its nose the most complex scientific instrument ever placed in space, a telescope with a primary mirror 6.5 meters across, made of 18 hexagonal gold-coated beryllium segments, folded for launch and designed to unfurl in space. A sunshield the size of a tennis court, made of 5 layers of aluminized kapton that would keep the telescope at the temperature of liquid nitrogen and below, making its infrared instrument sensitive enough to detect the heat signature of a bumblebee on the surface of the moon. Webb travelled for 29 days to its destination at the second Lagrange point, a gravitational balance point 1 million miles from Earth in the direction away from the Sun, where it orbits in sync with the Earth around the Sun. Its deployment was the most complex spacecraft deployment in history. 344 single points of failure, each of which had to work. All of them did. And in July 2022, NASA released the first images. The Deep Field image, the Carina Nebula, the galaxy cluster SMACS 0723, the spectrum of a hot Jupiter exoplanet's atmosphere, the Stephens Quintet, images of breathtaking clarity and depth that immediately revealed more than Hubble had seen in decades of comparable observing time. In the year and a half that followed, the confirmations came. One by one, the anomalies Hubble had spent its final years accumulating were tested against Webb's capabilities. The early massive galaxies confirmed. The overconcentrated dark matter in cluster cores confirmed. The overmassive early black holes confirmed and deepened. The little red dots, the population of dust-obscured AGN, invisible to Hubble, revealed for the first time. The stellar evolution anomalies, under investigation, with early results consistent with Hubble's indications. Each confirmation converted an anomaly into a fact. Each fact demands explanation. Each explanation requires physics beyond what we currently have. We are living through one of the most extraordinary moments in the history of astronomy. That is not hyperbole, it is a claim with a specific, defensible meaning. The history of astronomy has a small number of moments when observations outpaced theory so dramatically that the entire framework of understanding had to be rebuilt. Copernicus establishing the heliocentric model, Newton deriving the law of gravitation, Hubble establishing the existence of external galaxies and the expansion of the universe. The discovery of pulsars, whose periods were so precise that the initial discoverers, Jocelyn Bell Burnell and Anthony Hewish, genuinely considered the possibility that they were artificial signals. The discovery of dark energy in 1998, when 2 teams measuring Type 1a supernovae at high redshift found that the universe's expansion was accelerating. We are at another such moment. The observational picture produced by the combined legacy of Hubble and the first years of Webb is not consistent with the standard model of cosmology in a way that minor adjustments can accommodate. The discrepancies are multiple. They are independent, and they point in the same direction. The early universe was more active, produced more structure, grew more massive objects faster than the standard model predicts. The standard model, lambda CDM, the lambda cold dark matter model with a cosmological constant, is not wrong in the way that Newtonian mechanics is wrong. It describes a vast range of observations with extraordinary precision. The large-scale structure of the universe, the cosmic microwave background, the abundance of light elements. These are reproduced by lambda CDM to a degree of accuracy that any successor theory must also achieve. But something is missing. Something the model does not contain that the universe clearly does. And the search for that something, the theoretical work being done right now to accommodate the confirmed anomalies within a coherent framework, is where the next revolution in physics may be hiding. It may be dark energy that evolves rather than remaining constant. It may be dark matter that self-interacts. It may be new relativistic species in the early universe that affected the expansion rate before recombination. It may be modified gravity, a revision of general relativity that changes how gravity behaves on large scales. It may be primordial black holes that seed early supermassive black hole formation. It may be some combination of these or something none of these models have yet imagined. Whatever it is, Hubble planted the seeds of its discovery. By accumulating decades of data, by pushing to the limits of its aging capabilities, by sending back observations that didn't quite fit the model it had helped build, the model whose foundational constant carries the name of the astronomer whose telescope is named for. Hubble created the question. Webb is now interrogating the answer. The clock ticks on Hubble's re-entry. Sometime in the 2030s, most likely in the middle of that decade, based on current orbital decay rates, the telescope will enter Earth's atmosphere. It will not simply burn up. It is a large, dense object, and some components are expected to survive re-entry and reach the ground. NASA is working on plans to guide the re-entry to minimize risk, either through natural deorbit management or a potential commercial mission to safely dispose of the telescope in the ocean. But before that happens, Hubble may still contribute. Even in its reduced science mode operating on a single gyroscope, it continues to observe. Its ultraviolet sensitivity, which Webb does not have because Webb is an infrared telescope, remains unique. For observations of hot stars, of AGN emission in the UV, of the interstellar medium in wavelengths that no other space telescope currently covers, Hubble is still irreplaceable. It is still working, still watching, still in its final years, accumulating photons from targets that its successors will follow up on. The machine that has been orbiting above us since April of 1990 has not finished being useful. It is simply finishing. The countdown is not a cliff edge, but a slope, a gradual dimming, a slow handoff, the last pages of a volume that changed our understanding of the universe more profoundly than any instrument before it. And Webb, younger, colder, 1,000,000 miles further from home, immune to the atmospheric drag that is pulling Hubble slowly back to Earth, Webb will be watching when Hubble is gone. It will continue the conversation that Hubble started. It will answer questions that Hubble raised. And it will raise questions of its own that we cannot yet anticipate, because that is what the universe does when you look at it with unprecedented clarity. It reveals that what you thought was the edge of the story is actually the beginning of a deeper chapter. Lie here, in the dark for a moment. Above you, somewhere in its 95-minute orbit, the Hubble Space Telescope is still circling. The machine that showed us the deep field, the 3,000 galaxies in a patch of sky smaller than a grain of sand at arm's length. The machine that measured the expansion rate of the universe precisely enough to find it wrong. The machine that watched the deaths of stars across billions of light years, that mapped the dark matter in galaxy clusters, that found the first overmassive early galaxies, that saw Earendel, the most distant individual star ever observed, blazing in the early universe, already dead for 12 billion years by the time its light arrived. 1,000,000 miles away, in the opposite direction from the Sun, Webb is also watching. Colder, sharper, Seeing the universe in wavelengths that shift the light of the earliest galaxies into its field of view, like a radio tuned to a frequency no one had ever listened to before, confirming, one by one, the things that Hubble saw and could not fully explain, adding precision to anomalies, converting questions into facts. The universe is 13.8 billion years old. The stelliferous era has roughly 100 trillion years to run. The last black holes will not evaporate for 10 to the 100 years. Heat death, or vacuum decay, or whatever ending the universe has prepared for itself is so far away that the language we use to discuss it is barely adequate. But the questions being asked right now by the observations accumulating in Webb's instruments at this moment are questions about all of that, about the expansion rate that determines the universe's ultimate fate, about the dark matter that shapes every structure in it, about the black holes that will be its last organized objects, about the stars that are its current clocks. Hubble asked those questions first. And before it falls back to Earth, before it burns in the atmosphere over the ocean, before its components cool on the seafloor, it will have handed every one of them to the telescope that came after it. The countdown continues. The universe is stranger than we thought, older and faster and more structured and more extreme than our models captured. And the two telescopes that together have revealed this, one dying slowly above us, one watching perfectly from 1,000,000 miles away, have given us the most precise and most unsettling picture of reality that any generation of humans has ever had. It is not a complete picture. It is not a final picture. It is a picture that shows us, more clearly than ever before, exactly where the edges of our understanding are, and what lies just beyond those edges. The clocks are running. The universe does not wait.